All right, hello everybody. Welcome back to 10600 Math Background for Machine Learning. So let's see. You guys had some problems from the last class. I took a look over the answers that people gave. It looked like most people got them right at eventually. Some people had trouble with some, but not. It looks like most people eventually resolved their trouble. I got a request on Piazza to go over the solution to the Minesweeper problem, so I'll do that in a sec. If you guys have any requests for solutions to any of the other problems, or in fact any of the problems that we've done so far, just text the TAs and they'll let me know, and I can go over solutions either now or at the beginning of the next class. So let's go to the slides. All right, so here are the Minesweeper problems. So just as at a high level, the way these worked was the following. Let's see, because of this one right here, you know that there's a mine in either this square or this square. So either A or the unlabeled square next to it. So since there's a mine in one of those two squares, this one says that there's a mine in all of these squares, one mine in all of these squares. And so since you know it's here, it can't be in either B or the unlabeled square above B. And so that means that it's perfectly safe to click on either B or the square above B, right? And then there's a 50-50 chance that the mine will be in either A or the unlabeled square next to A. So someone wanted to know how would you write that in logic, right? So that I just gave the solution in words in natural language. How would you write it in logic? Well, okay, so let's label all of these squares. So we have square A and B already, so I'm going to label this square C and this square D, right? Like that. This one gives us a constraint that there's a mine in square A or C. So you would say A or C, right? And it also gives us that there's at most one mine in square A or C. So you would have not A or not C, right? So those two constraints come from that one right there, right? Then from this one, right, there's you get the constraint that there is a mine in A or B or C or D. And then you get that there's at most one mine in all of those squares. So to do that, you can't write that the at most one in just one constraint, but you can write it in several. So we know, for example, that there can't both be a mine in A and C, so not A or not C, same as before. We have not, sorry, I should probably write a little bit bigger, so I'll try and do that. Not A or not B, not A or not D, and then the same thing, not B or not C, and not D or not C, and finally not B or not D, right? So these are, right, you get all of these constraints from this one right here, and it says that there's at least one mine in the squares A, B, C, and D. And for any pair of squares, A, B, C, and D, there can't be a mine in both of them. All right, so then, then we should be able to use all of these constraints together to say that there won't be a mine in B or D, right? So in particular, let's say that we want that there's not a mine in B, right? So one thing that we could do is we could do resolution. Let's see on that one, right? So we can resolve not A with A, and we can get C or not B, right? And then we should be able all right. Actually, at the moment, I'm not seeing the. I apologize. I thought I had gone over this in my head. I'm not seeing the path of resolutions that I need to make this work. So what I'll do is I'll post a longer description of this on Piazza. But you can see basically how we want to set up the problem, right? We set up all of the logical constraints, and then we're going to use our inference rules to show that there's not a mine in the square B. All right. So that's that. I haven't gotten any requests so far to solve any other problems, so we'll just go ahead and move on to the lecture topics for today. So at the end of last lecture, we started going through these lecture notes that I'm about to put up on screen. All right, so here we go. I'll make that bigger. So we were talking about how to, well, that's maybe a little too big. Let's make that a little smaller. All right, so we were talking about how to work with probability tables, right? So we have factored form for representing a probability distribution. And so here the example that we gave of factored form is this one right here, right, where we have a table with 5 arguments. So that's a 2 by 2 by 2 by 2 by 2 table with 32 entries. And we represent it as a product of a whole bunch of other smaller tables. And the product has kind of an interesting semantics. So let's go down to some of the tables here, right? So here are a couple of the tables that we have on the right-hand side. Here's a 2-element table, probability of O, and here's a 2-element 1-argument table. This is an 8-element table because it has 3 binary arguments, 2 to the 3. And so we have to figure out how to combine a bunch of tables like this in order to get a table that has 32 entries. And the rule basically is that if you, what you want to do is you write out the large table that you're trying to get. So that is a table over the values of 5 different random variables. You pick a cell in that large table, and that cell corresponds to an assignment to all 5 of your variables. It might be that W is true and O is false and R is true and so forth for all 5 of the variables. And so then you can look up in your expression, right? We had an expression here For each one of the smaller tables, you can use your assignment to look up an entry of that table. So for example, in the P of O table, you look at the value of O in your assignment and you use that to choose an entry of your table. Now there are a bunch of other variables in your assignment and those don't matter. You don't use them when you're looking up in P of O. And then similarly in P of W given O and R, right, what you can do is look at the values of these three variables, W, O, and R, and use them to look up a value in this table. So if we go back down here, let's say W is true, that corresponds to the top half of the table. Let's say O is false, that corresponds to the bottom row of the top half. And let's say R is true, so that's the left entry, and you'll get 0.1, right? And if you do that for all 5 tables, you'll get 5 numbers, and then you multiply those all together, and that's what you get as your value in the large table, right? So this is, the rules are straightforward, but you should practice with them so that you get sort of a feel for how they work. All right. So another way of thinking about it is as operations. So what I described before was how to think of the operations element by element. But you can also think of it as operations on the table as a whole, and some people like to think of it in these terms. If you want to think of it that way, what you can think of is, okay, so here's a small table, right? So let's say we're just going to add 2 tables together, right? So here's the smaller table, here's the larger table. The smaller table has only x as an argument, and the larger table has x and y as arguments. And what you do is you essentially replicate this smaller table. You put 1, 2, 3, and then another copy next to that of 1, 2, 3, and then you add those 2 tables together element-wise, right? Here we're adding. In the previous expression we were multiplying. It doesn't matter, you just do all of the operations component-wise, right? And so this behavior of taking a table and replicating it along a dimension that it doesn't have, that's called broadcasting. And some people like to think of it in those terms. And you can think of it whichever way you want. If broadcasting is easier, think of it that way. If you thinking of it as element-wise doing lookups, then it's easier to think of it that way. And you can either way, you can use that to understand what the expression means. All right. So, all right, let's go back now to the slides so that I can write. I'll take this away. All right. So, when we have a distribution in this factored form, we definitely want to be able to manipulate it, right? We would like to be able to work with the factorization and change it around. So, for example, re-expressing it in order to be able to understand different properties about the probability distribution. The single most important rule for doing that is the chain rule. The chain rule says that for any joint distribution, P of A comma B, right? And remember, the comma means that it's a distribution over both of them, so it's probability distribution with 2 variables. That's equal to P of A given B times P of B, right? And that follows from the definition of conditional probability. The argument for that is in the lecture notes. Take a look at that if you don't remember it. But for example, if we had a distribution of this form, P of A, P of B given A, P of C given B, right? And so sometimes it's useful to draw a little graph of what's going on here. If we have what happens here is we have a variable A, and then using the variable A, we find the variable B. That's the arrow means that B is conditioned on A. And then the same thing, C, right, is conditioned on B. So we can refactor this, right? P of A times P of B given A, that's the same as P of A, B, right? And that is also the same as P of B, P of A given B, right? And then we can take P of B and P of C given B, and that's the same as P of B, C, which is also the same as P of P of B given C, P of C, right? So I can take this and I can say that's equal to P of C, P of B given, not A, but C, and then P of A given B, right? And so now I'm thinking of C first, and then determining B from C, and then determining A from B, right? And so these two representations, they're completely equivalent, right? I can, if my distribution started out written in this factored form here, I've used the chain rule a couple of times to show that you can also write the exact same distribution in this other factored form here, right? And so that's useful. That means that we can go back and forth between different factored forms of the same distribution. Now, from the chain rule, we can derive Bayes' rule, right? I'm not going to, again, the derivation's in the notes, but Bayes' rule says that P of A given B is equal to P of B given A, P of A, let's make that a clearer paren, over P of B, right? So that's Bayes' rule. Remember this, right? You'll be using it a lot. And the homework that you guys are working on right now has a bunch of uses of Bayes' rule in it, right? Like you'll need Bayes' rule in order to solve the homework. And in particular, there's a version of Bayes' rule that you will see often, where you don't need to know this denominator ahead of time, right? So the denominator here, P of B, it's sometimes useful not to have to know it ahead of time. And so let's take a look at the exercise that's in the lecture notes. Again, this was not an exercise that you guys had to do, but I want to, hopefully you thought about it, and I'm going to go through the solution now. So we have two variables, G for grass is wet and S for sprinkler is on, right? And if we have P of S equals 1/3 or 2/3 for whether S is true or false, and then P of G given S is equal to, well, one of two things. So G is the first argument, the row of the table, and so we could have the distribution 3/4, 1/4 for the grass being wet or not. That's if the sprinkler is on. And if the sprinkler is off, it's 1/5 and 4/5, right? So now what we want to know is, suppose that we observe that the grass is wet. What's the probability that the sprinkler is on, right? So this is a probabilistic version of a common logical inference rule, right? You've seen a consequence, you've seen a possible consequence of the sprinkler being on, namely that the grass is wet. So you see this consequence and you want to reason back to see what the chances are of the cause being true. And so you can use Bayes' rule for this, right? So P of S given G, right, is equal to P of G given S, P of S over P of G. right? And we're given these two terms in the numerator, right? P of S and P of G given S, and we weren't given P of G, right? But we don't need to know it. We'll just work it out later, right? So for right now, what we'll do is we'll replace it by some unknown factor we'll call eta, P of G given S, P of S, and then we're going to figure that out later. Right? So now we can start filling in, right? P of S given G is equal to eta times the following table, right? P of G given S, P of S, right? So this is the, just going to label, right, that the rows are G and the columns are S here, right? And here, S given G, the convention is to do the first one as the rows, right? So this would be S as the rows and G as the columns. So we'll take this here and we just transpose it, right? We flip the order of the arguments. So 3/4, 1/4, 1/5, 4/5, right? And then we multiply that by P of S, right? And P of S is 1/3, 2/3, so it's 1/3, 2/3. And again, we just broadcast 1/3, 2/3, right? And so this is equal to eta times 3/4 times 1/3 is 1/4. 1/5 times 2/3 is 2/15. Quarter times 1/3 is 1/12. And then 8/15, right? And now I'm not going to do the arithmetic here because my adding fractions is a skill that's atrophied since I got a copy of MATLAB. But we know now sorry, I wrote this slightly confusingly. It should be, let me erase this. We know, so P of S given G, we know each one of these things has to be a probability distribution. So we'll call this eta 1 and eta 2, right? Eta is a table. Eta 1 and eta 2. Sorry, and this is eta 1 again, right? And then this is eta 2 to make that normalize, right? And so here, eta 1, eta 2 times that, and eta 2 times that, right? And so we know, for example, that okay. So let's, we're getting a couple of questions. Let me just finish this thought here. We know that 1/4 plus 2/15 times eta 1 is equal to 1. And so we know that, well, 1/4 plus 2/15, common denominator is 60, lovely. So we'll just say 15 plus 8/60, lovely, times eta 1 equals 1. So eta 1 equals 60/23, right, in order to make that happen. And then there's a similar way that we can calculate eta 2 to make the columns sum to 1. And again, I would make MATLAB do that calculation for me, but I just wanted to write out what we needed to do. So there was a question about why we transposed. So the convention, when you write out a table for a probability expression, you just take the variables in the order that they appear in the expression. So G appears first, so it's the row index here. S appears second, so it's the column index here. We asked for S given G, so now S appears first and G appears second. S is the rows and G is the columns, right? So we just swapped the order of rows and columns. That's exactly the same as transposing, right? So we had to transpose this table just to get it in the order that we needed the arguments of that table. All right. So just to quickly recap, right? We have our two givens, the probability of S and the probability of G, right? P of S given G is equal to P of G given S, P of S over P of G. And so we're just going to write P of G, that's a two-element table, or 1 over P of G, as a variable eta that we're going to figure out later. And eta is a table that has two elements, eta 1 and eta 2, right? And so we'll just, this here, we'll copy it out, but fill in the P of G of given S and P of S that we know. So P of S given G is this, right? Our eta table, eta 1 and eta 2, right? Because we know that these two together normalize to form a probability distribution, and same with these two. And then the elements from P of S, that's the first fraction in each one of these products, right? It's copied from this table up there. And then, so that's the P of G given S elements, and then the P of S elements are the second fraction in each one of these products. And then we can solve for eta 1 and eta 2. And just to prevent I'm just going to write that out more clearly. 8 over 15 times eta 2, right? And then we can solve for example, eta 1, if I did my math correctly, should be 60 over 23 to make everything normalize to 1. All right? So that process of starting out with a prior, so here we're asking what's the distribution of S, is the sprinkler on, given some evidence whether the grass is wet. We start out with the prior information, P of S, about whether the sprinkler is on, given no information. Then we multiply in a term that corresponds to evidence that we've gotten. We've seen that the grass is wet, and that tells us something about whether the sprinkler is on, right? And then we normalize to make everything be valid conditional probability distributions. So that process of incorporating evidence, that's one of the most common uses of Bayes' rule, and it's going to happen over and over again in machine learning. Right? So I would encourage you to write out this example, this simple example again, and go over it, make sure you understand it. And there are, in the homework that's due on Friday, there's the question about Alice and Bob, whether Alice is caught up. You can use Bayes' rule to incorporate evidence in exactly the same way. In a given week, we know that Alice has some probability of being caught up and some probability of not. And then we observe whether she calls Bob, and that gives us some more evidence about whether she's caught up or not. And we use Bayes' rule exactly like this to incorporate that evidence. All right. So another idea that's going to be important is independence. Right? So we're using this factored form of a probability distribution. And one of the things that we can read off sometimes from a factored form is whether two random variables are independent in this probability distribution. In particular, if we can split our distribution into a product of some terms that depend only on one of the random variables and then some terms that depend only on the other one, then that tells you that those two variables are independent. And if no such factorization is possible, then they're dependent. And there are some examples of that in the lecture notes. Maybe slightly, it's the same concept, but slightly more complicated application of it is conditional independence. So remember, we have if we have a distribution over a bunch of variables, we can condition on an event, or we can condition on values of a random variable, and that will update the distribution over the remaining variables, right? In general, the probability will be different after you get some evidence. So in that new distribution, after conditioning, two variables could be independent or not. If two variables are independent after conditioning, they're called conditionally independent. And it's important that conditional independence is not the same as plain, also called marginal independence, right? Two variables can be marginally independent and conditionally dependent, or vice versa. And again, there's a way to check conditional independence by looking at factorizations. And that's something that if you take the machine learning course on graphical models, there are reams that you can write about the techniques for manipulating a factored form to be able to tell whether two variables are conditionally independent. But there's a simple example of it in the lecture notes, and so we'll stop with the simple example. All right. So that's the end of the lecture notes on factorization. Again, if people have questions about that, please ask the TAs or post it on Piazza, and I can go over any questions that people have. Whoops. Cancel. So let's move on now to the next set of questions, the next set of lecture notes. So we're going to talk now about mean and variance. And these are ways to summarize the distribution of a real valued or of a number valued random variable. So the mean is just the average that you expect to see if you sample a whole bunch of copies of that random variable and average them together. And the variance is a measure of the spread around that average. So the formulas for mean and variance are in the lecture notes. I'm not going to go over them unless people have questions. But this idea of one idea that might require a little bit of thinking about. So let's say we have a random variable. Let's say the number of spots on a die roll. We'll call that x, right? So x is going to be 1 through 6, unless you're using one of those polyhedral dice that I've spent way too much time rolling. But let's go back with, let's stay with the ordinary 6-sided die. And so we can ask for the mean of x, right? And the formula for the mean is just the sum over all possible values of x, the probability that x is equal to x, times x, right? So that's going to be all of the probabilities are 1/6, right? And so if you happen to remember, the sixth triangular number is 21, right? The sum of 1 through 6 is 21, and so this is 21 over 6, right? Which happens to be 3.5. So the mean of a die is 3.5, but remember random variables were interpreted as a function on our set of atomic events. So here our atomic events are just the numbers 1 through 6, and this particular random variable is just the identity function, right? So let's write x of little w, right? So w is an atomic event, is just equal to w, right? Now, we can ask about a different random variable, right? If x is a variable, then x squared is also a random variable. And this is, in particular, we can think of x squared of w, right? It assigns a value to every atomic event, and that's just w squared, right? And in particular, what we've done is we've taken the function that maps, you know, a number to its square, right? And we've composed that with the function. We've composed that with the function x, right? And we've gotten a new function, right? So x squared is equal to the composition of the squaring function with our original random variable, and so x squared is a random variable if x was. So this is just a little bit of practice of thinking of random variables as functions that take in an atomic event and give you out a number. You can think of this without thinking about the atomic events, and maybe that's a little simpler some of the time, but it's always worth remembering that there's an atomic event under there somewhere whenever you're thinking about a random variable. All right, so now we have a new random variable, x squared, and we can ask for the mean of x squared, right? And so we'll write that e of x squared, right? And again, that's just the sum of the probabilities, and all the probabilities are a sixth, times the possible values. So 1 plus 4 plus 9 plus all the way up to 36, right? And I'm not going to work that one out off the top of my head, but you could ask MATLAB to work that out for you if you wanted to, and you'd get the expected value of the random variable x squared. And so we can take expected values of all sorts of different things, and that's going to be a very useful thing to be able to do. When we work with expectations of functions of a random variable, one of the things that will be pretty useful to know is linearity of expectation, right? So e of ax plus b is equal to a times e of x plus b. So we can just take a linear function out of an expectation. For example, if we take suppose we wanted to know the value, suppose we want to know the expectation of 3x squared, right? So again, if x is a random variable, then 3x squared is a random variable. Well, that's equal to the expectation of 9x squared, which is equal to 9 times the expectation of x squared, right? And so now what we've done is we've related the expectation of this random variable to the expectation of our original x squared random variable. So again, linearity of expectation is a pretty useful tool to be able to work with things. And in particular, that will be useful when we're calculating variance, right? So the variance written the variance of x, or sometimes just v of x, that's defined to be equal to the expectation of x minus its mean squared, right? So here, the expectation of x, this is a constant, right? It's not a random variable anymore. Once you take the expectation of a random variable, it doesn't depend on what value that random variable takes. It's a property of the whole distribution. So this here is a constant. So this is random variable minus a constant squared, right? And so, for example, we could work with this expression and write something like e of x squared minus 2x e of x plus e of x squared, right? And then we could use linearity of expectation to say that this is equal to e of x squared minus 2. E of x is a constant, so we can pull it out. 2e of x times, now we have just the expectation of that x left in there, plus e of x squared, right? And again, here e of x times e of x is e of x squared, right? So this is now e of x squared minus e of x squared, right? So this sort of manipulation of an expression involving random variables and expectations is the sort of thing that you should be able to do fluently. And so I went through this example as an example, but if it took you a little bit of effort to follow that, then I would recommend going through it and going through maybe some other examples. So a good example of that you could go through would be the one that's next in the lecture notes, the variance of a coin flip. You should be able to convince yourself that the expression that I gave in the lecture notes for the variance of a coin flip is correct. Now, there's also a definition of covariance in the lecture notes and of correlation. I'm not going to go over those. I just wanted to mention that you should know what they are. And just like I was saying before about conditional distributions, you can have, after you condition on something, an event or a random variable, you can have a mean or a variance of the distribution that you get after conditioning, and those are called a conditional mean and variance. And there are some examples that you'll be doing in the problems, and so you want to be able to make sure you understand what a conditional mean and variance are, and that you're able to calculate them. Finally, the last thing that we want to look at for means and variances are what are we going to do with a vector valued random variable, right? So far our random variables have had values like 3 or 7, right, or blue, right? They've been discrete or numeric valued random variables. You can have a random variable can take values in any set that you like, and so in particular you can have a random variable whose values are vectors. And when you have such a random variable, you could ask for its mean and its variance, right? And the mean of a random variable, of a vector valued random variable, you just take it component wise, right? So if you have a random variable x, which is a vector with 2 elements, x1 and x2, right? E of x is just equal to the vector whose elements are e of x1 and e of x2. Right? For variance, it's a little bit more complicated. We actually define an entire variance matrix, right? So again, if x is equal to x1, x2, then the variance of x is defined to be the following matrix, right? And I'll write it out in its interpretable form first. Just the variance of x1 and the variance of x2 go on the diagonal. And on the off diagonal, we get the covariance of x1 and x2. And that's symmetric, so it's on both off diagonal elements, right? And the formula in general is that v of x is equal to the expectation of x minus e of x times x minus e of x transpose, right? And you can verify that these two definitions lead to the same answer. Convincing yourself of that might be a good thing to do. And we're not going to do it right now, but later on you'll see that you can use the variance of a random variable to tell you a lot about its distribution, the variance of a vector-valued random variable. All right, so let's see. So I published on the syllabus page a set of exercises that are due at the beginning of lecture next time around, so the beginning of lecture on Monday. There are a few more problems than I wanted to make due midnight tonight, so I just wanted to give you until the beginning of next lecture to do them. You guys should all be able to go and have a look at those. And what I'd like to do right now is just wait for a few minutes and let people take a look at those problems, and possibly we can go ahead and answer any questions that people have about those problems here and now, so that we can avoid having people be confused longer than necessary. And these are all questions about the stuff that we've talked about so far in lecture today: conditional distributions, Bayes' rule, means, conditional means and variances, that sort of thing. So I'll just shut up here for a little while and let people take a look at these problems. All right, so people are telling me that I cleverly pasted in the link, the wrong link to the exercises. So give me a minute or two and I will fix that and post it on Piazza. Sorry about the confusion. All right, so sorry about the hiccup. It looks like we fixed the link. This is on the syllabus page. There on the line for the date of this coming Monday's lecture, because that's when they're due. So for people who are looking at the first couple of problems, one hint for those is that the entire joint probability distribution of those three random variables is only an 8-element table. So what I would suggest is that you take your favorite programming language and you use it to construct that entire table and then marginalize and condition, do the appropriate operations on the table to get the answers that you want. Hey everybody, so I just wanted to check back in. I've been watching on Q&A and most people have not had a chance to look over the entire problem set yet. So what I'm thinking is rather than starting a new set of lecture notes, there's a new set of lecture notes posted for this Monday's class. I'm not going to get started on that. Instead, we'll just wait the remainder of the class and answer any questions that people have about the problems that I just posted, because there's no point in going on to a new topic while people are still worrying about the old one. So please make sure to ask questions. Hopefully we can clarify any problems that people have before the end of class today. If not, please ask on Piazza or come to one of our office hours. Thanks. Hey everybody, so I'm getting a question about notation. So let's go and look at that. So the question was about these two notations. We have one notation, P of G equals T, given R equals false, S equals true, right? So here, this notation talks about a single number, right? It talks about the probability that this event happens, G is true, given that this event happens here, R is F and S is true. Then there's also this notation, P of G given R comma S, right? This is a table, right? This here is in R, and this here is in R 2 by 2 by 2, right? And so this is a table of all of the possible values for whether G is true or false, R is true or false, S is true or false. And you can mix these, right? So you can ask for P of G equals true given R comma S, right? And this is in R 2 by 2, right? Because it's got two variables that you're trying to set to all of their possible values, and one variable that you've filled in a value for, right? And so, for example, this P of G given R equals true comma S, right? What would that be? Well, this would also be in R 2 by 2, right? Because S and G here are free, right? And R is bound. So there's two free variables and one bound. And to get the size, you just count the number of free variables, the ranges of the free variables. Hopefully that clears up the notation question, but please ask some more if that isn't clear. Thanks. All right, guys, I think we're gonna wrap up the stream. We're getting a few more submissions on this problem set that I just sent out. Please continue to have a look at it and ask any questions that you have on Piazza, and we'll or come to office hours, and we'll do our best to answer them. Thanks, and see you guys on Monday.